For arithmetic operations in a polar coordinate system, it is often easier to do multiplication and division in these systems. And just as a quick refresher, our polar system means that for this particular quantity x, it has length of a and then an angle of phi 1. So this particular quantity right here would be x. So if I want to multiply x and y, it's a standard sort of straightforward operation of combining my terms. And so if one was to multiply both of these, the result would simply be a times b, because those are our coefficients on the outside. And then because these objects have the same base for their exponents, we can just add the exponents together. And so the result would be e to the j phi 1 plus phi 2. Remember, when you're multiplying elements that have the same base in their exponentials, you just add the exponential components. And so in the same way, if I were to, let's say, divide these two quantities, it would be a e to the j phi 1 over b e to the j phi 2, and my result would be a over b e to the j, and because they are divided, I will subtract the two components rather than add them. So the operations right here, if your value is already in a polar system, is rather straightforward. What actually becomes complicated is what happens when we try to add these two elements. What happens if I try to add this one to this one? There are really no like terms that we can combine. There's nothing that we can pull out and kind of simplify. So often what we will do is if we need to do a multiplication or a division operation, we will either move it into a polar system or keep it in a polar system. If we need to do addition and subtraction, we will move it into sort of our vector and rectilinear space that we looked at before.